Last time we talked about the miscible fuel. That means that a fuel with at least two components, and those different fuel can well mixed together without any addition chemical. And I tell you, there is a very important inference coming from the Lewis number of liquids, since for liquid Lewis number is always very big. That means the thermal diffusibility is much stronger than the mass diffusibility. Heat easier to transfer into the interior of the liquid droplet, but the mass, if you have a two component fuse together, then you will find out that one of the component it is very hard to diffuse from the center to the surface. And those kinds of behavior, the inference coming from the Lewis number on the multi-component droplets become more significant if you choose the two components with the big difference on their boiling points. And last time we give you the examples when you mix the C7 and the C16 two liquid fuel together, because they can miscible together. They are miscible and easier to mix together, but they have a big difference on boiling point. Actually, the boiling point for 16 is almost double compared with that for C7. And when you do the experiment by changing the composition of 16 from 10 to 40 and to 80, you try to increase the amount of the large boiling point of fuel, then you will find out there is a very interesting behavior could be observed from the experiments. Okay, and you can see if you look at the knife, for the B case, you find out there is the flattened regions to see almost no droplet size variation in this short period. Initially, you can figure out there is the linear decreasing curve, and in the final portion, actually, they still show the same linearly decreasing line. Here, both of them fit with the D-square very well. But in the middle branch, they show you a flattened line. This means that in the initial period, actually, the evaporation is controlled by C7 with lower boiling points. Okay, but when you evaporate most of the C7 from the surface out, then on the surface of your droplets, you just have a C16 field left on the surface. But in the middle, in the center, in the interior of the droplet, actually the percentage of C7 and C16 almost no change, because for the C7 in the center of your droplet is very hard to transfer to the surface to support the burning. Therefore, the rest of the fuel on the surface just remains on the C16. Then you need to heat it up, because the boiling point is are quite different between these two C7 and the 16. Now on the surface, you just have a 16 left. Then you need to wait the temperature increase to the boiling point of the C16. And in this moment, actually, this short periods, the heat coming from the diffusion flange will be used to support the preheating of 16. And this moment, since those heat just used for preheating, no gasification occurs. That means the droplet size is almost no change. Then you can see there is the flat form occurs in the middle region to tell you the droplet size is almost no change. And this is the behavior concerning the droplet size change. In the experimental observation, you still can see the other very interesting effect. You can see the flange size is become smaller, shrinks. They will move closer to the droplet. This is easier to understand, because at that time, in this short period, all the heat used to supply the preheating of your C16 to his boiling point, and they do not have enough fuel vapor coming out to support the outer diffusion flame. Then you understand the position of diffusion flame will change its own position to closer to the supply of fuel vapor site, right? Because the fuel vapor supply become weaker. Now the flame will shift to the liquid surface, and we call this as the so-called the flame shrinkage phenomena. And these behaviors actually they were enhanced by increasing the percentage of 16 and we'll move to the initial period. And I mentioned when you add the 80% 16s, you will find out in the earlier periods, the line become a more curve, do not show you the linear decreasing lines. This tell you in this short periods, actually you can evaporate the 20% C7 very fast from the surface of your liquid. But the rest of the 80% C16, at that moment, they start to absorb heat for preheating. For preheating, therefore, all the vaporization of 16 Cs, and they do not give you the linear decreasing behavior described by D square law. Those kinds of behaviors sometimes will be enhanced, and to show you the other very interesting behavior we call this is a micro explosion mechanism. Okay, how to dealing with the micro explosion mechanisms? Let's look at the structures that there is a detailed description based on our slides, but I try to give you some explanation on that. You try to think about now you have a two components liquid fuel, and these two components they have a very big difference on their boiling point. Okay, even higher the differences between boiling point even higher than previous case C7 and C16. Okay, in this case you will figure out in the initial period, suppose you will evaporate certain amount of the low boiling point fuel out. Therefore, most of the fuel exists on the liquid surface are higher boiling point materials, right? In this moment, as I described earlier, you need to spend certain time to heating up to their boiling point, then they have a chance to start to evaporate. In these short periods, the heat continue transfer not just to heat the liquid on the surface to increase the temperature, they still can penetrate into the interior of your liquid droplets. Okay, but you remember inside of the droplets, they still have the low boiling point material in center region. They continue to absorb heat on the surface. The higher boiling point fuel, the temperature for that is increased. Also, in the interior of your droplet, the lower boiling point materials they still absorb heat, but you can understand it is easier to be the temperature is easier to be higher than its own boiling point, which means in this transfer the heat transfer process inside of your liquid droplets, the lower boiling point fuel they start to evaporate. Okay, they can gasify before the condition at the liquid surface for the higher boiling point fuel. That means that in the process you can see they have some gasification of the fuel inside of the interiors. And you remember initially those kinds of low boiling point liquid fuel is confined by the liquid itself, right? It's a free surface, and the region basically the volume is controlled by the liquid volume. But when the liquid gasified, that means the change from the liquid to the gas, the volume in general, if you do not have a boundary, the volume of a gas is almost 1,000 times of the volume of the liquid when they gasify, right? Thousands times, that means there's a big volume. But in this case, those kinds of expanding volume actually is restricted as their previous volume, liquid volume, which means that if you cannot expand your volume, now instead you will have the pressure buildup, right? Okay, in this case, now the original liquid boiling contains a vapor with high pressure. When this pressure is high enough, then they will push the boundary out, then make the whole droplet be broken, right? This is a so-called micro explosion. Okay, let me read through it, and you can quickly understand, follow the sentence. And here they say, shortly after initiation gasification, the droplet surface become more constant with less volatile high boiling point component. Okay, that means they need to go through the preheating process on the liquid surface. Now, since the droplet temperature is controlled by its surface composition, it can therefore reach very high values. On the other hand, the drop core, that means the in the interior of droplet, they still have the lower boiling point field exists. The drop core has a higher concentration of the more volatile low boiling point components. Therefore, the volatile components in the droplet interior can be where is that? The more volatile boiling point components, then the volatile component in the droplet interior can be heated beyond the local point boiling point, and hence start to accumulate sustainable amount of superheat. This may emphasize the control boiling. Actually, the boiling do not change, but they accumulate a large amount of vapor. Then they do not have some expansion. Indeed, they need to have built up their pressure. Okay. Then they say the extremely rapid rate of gasification leads to intense internal pressure buildup, and thereby the catastrophic fragmentation of the droplet. They will break the older droplet into to the very small parts. And this evidence can occur in less than 2 times 10 to minus 4 seconds experimentally. This is a very short time. That means that when the buildup of your superheat vapor of the lower boiling point components inside of the droplet will produce a high pressure to make the structures of the whole droplet to become so many tiny droplets. Okay, this is the sequence, the process for the so-called micro explosion for a multi-component droplets. Okay, in some applications, they meet those kinds of requirements in using the micro explosion mechanism. We think about how to figure out it. Actually, for a combustion chamber in practical applications, they have a long combustion chamber because the heating material require a long distance to achieve their thermal heating requirements. Now, when you are thinking about there is the long combustion chambers, then you apply spray into your combustion chamber, you will figure out there is a 2 point. The first point you think about, can we extend our flame as long as possible to fulfill the length of combustion chamber? Then you understand if you have a large droplet, that means this droplet is a large momentum to move from the injection point to the end of the combustion chamber. That means the droplets should be large enough. Okay, this is one of the criterion, large enough for penetration into combustion chamber. But there is another thinking is you need to have a smaller droplet, because a small droplet, that means that you will increase the total surface area for the liquid fuel to gasify to produce a vapor, then mix well with the outer surrounding oxygens, then go through combustion. That means that small droplets will give you a good and a rapid gasification, and you will provide a complete combustion and make the whole combustion will be complete. Therefore, you will usually you will prefer to have some the group of the droplets has a smaller size. Okay. Now the thing is, when you look at these two criterion, you need to have a large size droplet, right? But you prefer to have a small enough droplet size for a complete combustion. But they are contradictory, right? But how to do this? How to make your droplet can move from the injection point to a long distance at the end of the combustion chamber and still keep a good combustion behavior. Now people think about it. Can we do it? Sure, if you try to apply your micro explosion mechanism into your spray. Then you think about it. Initially, you may have a large droplet, right? And this droplet can have some large momentum to move its own to a longer distance, maybe at the center and the major heating area of your combustion chamber. Now, droplet size is still large enough, but they already experience the certain heating. In this period, the fuels, because now you are use the multi-component fuel, right? The low boiling point fuel inside of your droplet, the large droplet, they already becomes a vapor, they build up the pressure. At this moment, they start to have an explosion. When they have a micro explosion, that means that this big droplet produce so many tiny droplets. They make the possibility for replication and a combustion in this region. Okay, this is the idea. Therefore, they tell if the micro explosion can be controlled to occur after penetration is achieved. Okay, go to the major combustion region, this big droplet, then this big droplet can break up itself to make so many tiny droplets. Then the rapid gasification will give you a primary concern in design the spray. I'm sorry. Then this can be achieved. Okay, because you use a micro explosion automatically can occur and break up the large drop to small droplets. Okay, then the rapid gasification need not to be a primary concern in designing the spray system, which means in this kinds of optimal droplet size designs, you try to use the micro explosion to achieve both of the criteria, large enough and small enough for the combustion chamber, complete combustion applications. Okay. The second part, the micro explosion is good for the improvement on utilization of synthetic and less uh, refined fuels, which generally have a higher boiling point ranges. Usually, when you have a less refined fuel, that means the composition has a higher boiling point, and usually they have a higher viscosities and it is not easy to break it apart from the atomization of the liquid fuel to make a tiny droplets. They are not easier to be gasified and burning. But if you try to mix well with the other lower boiling point fuel, then you can have those kinds of micro explosion behavior and try to make this big droplet break apart and to automatically produce small droplets. And this is a typical image for your reference. Here, this tell you this is a binary nucleation of two. You can see this is a big droplet, right? This is a dimension for 1 millimeter. And then you can see there is a two bubble occurs in the inside of the droplet. Okay, and this show you there is some vapor built up in this small area, and later on, if the pressure still increase, the gasification still continuous. Vapor coming out with the higher pressure, then they will push the boundary because this is a free interface. They have a strong pressure, then push it up, then they will produce tiny droplets. Okay, and there is these two picture to tell you there is an example in the middle picture that represents weak fragmentation due to the fuel impurity. If you have if your fuel has some impurity in the combustion process, sometimes they will have some kinds of impinging out. Okay, the break of the droplet. There is a small increase of the flame surface. Okay, and this is a big one, strong micro explosion due to the superheating of the more volatile. These pictures taken from the experiment from the free-falling droplet experiment. And some literatures give you the to show you there is a strong micro explosion. For example, they tell you the diameter of fireball, which means it's when you have micro explosions, the diffusion frame will become larger since the droplet was broken to many tiny droplets. At that instant, the frame will be extended to a large to have a large frame radius. You can see from their experience when you burn the 90% hexadecane with the 10% H-butane. H-butane contains certain amount of nitrogen, and this nitrogen additive actually has a very strong explosion behavior. Okay, here this is a C4H9N3. Okay, and this will when they have a micro explosion, they find the diameter of fireball is almost 50 to 100 times of original droplet without micro explosion, which means at least the power for micro explosion in some applications are very strong, and to be used to have to make a small droplet in the major combustion region and to achieve the complete combustions. Now we go to the next step. In the previous part, we look at the miscible fuel, but the next part, sometimes you will need to mix the two liquid together, but they are not immiscible. They are immiscible. Okay, they cannot mix well directly. Now we say we can use some surface chemical surfactants to try to help them to combine these two liquids together. Then we call this a so-called emulsified fuels. And this emulsified fuel, the most important application for emulsified fuel, basically, we try to use water to mix with oil. There is why we choose the water mixed with oil. There is the two reasons. The one reason is when you have a water mixed with a fuel together, water usually they do not contribute any heat release for the combustion, right? But you remember water can absorb certain amount of heat in the combustion process. That means that this application will reduce the temperature distribution inside of combustion chamber, then has a possibility to reduce the thermal NO. I will explain later for the those kinds of emission for thermal NO. Thermal NO actually coming from the temperature. If the temperature of your combustion chamber higher than 2000 K, then the nitrogen from the air, usually nitrogen is quite stable without participation to the combustion. They just absorb heat. But when the temperature is too high, actually the chemical chain of the nitrogen will be broken. Then they will have some nitrogen atom release. When you have nitrogen atom release, they will meet oxygen atom, then they will produce the so-called NO. Okay, then this is a cause for the thermal NO, basically coming from the temperature is too high. Then we use water in the mix with oil. Then when you bring those kinds of emulsified fuel into your combustion chamber, then water will place the heat absorption low and try to reduce the local temperature as lower as possible, lower than 2000 K. Then you can prevent the production of thermal NO. This is one reason. The other reason is water has a very low boiling point compared with the usual fuels. Then you can see water is around 100 degrees Celsius, right? Then the oil usually have a 200, 400, and 300. Then they have a big difference on the boiling point. The water is easier to have this emulsified fuel to have a micro explosion. Okay, these two reasons that people try to use emulsified fuel, especially use water as the lower boiling point liquid to make this higher boiling point of fuel. Okay, and when you use the water mixed with oil, then we usually say WO immersions. W means water, O represents different kinds of oil. But those kinds of mixing between the water and the liquid fuel depends on how much energy you supply into the mixing process. Usually, they will mix the certain amount of chemical surfactants to have the molecule of water and the liquid fuel. They can well mix together, but they need to apply different kinds of mixing energy. If you use less mixing energy, actually the mixing basically based on the so-called what we call this is the macro emulsions. The mixing basically the, will stay in the label on the droplet size around a few micron. Okay, then when you have those kinds of mixing, that means that they still the molecule of water and also the liquid fuel, they remains still a droplet size, very tiny droplet size around few micron. Then you can see they were reflected from the light source. You will find out it's some kinds of milky appearance. The light cannot penetrate into the droplets. Okay, and then you just can see it's a milky appearance. Okay. Then, if you try to increase your mixing intensities, then the mixing label will go to a few hundred Armstrongs. Is much lower to the size scale. Then the older droplet, the appearance becomes transparent. Okay, and here we call this as a micro emulsions. Okay. The difference between the macro and the micro emulsions is just this, depends on degree of mixing. The micro explosion, the mixing is relatively go to the small scale, a few hundred Armstrongs. But for the macro emulsions, they just mix at a few micron scale label. Okay. Now let's look at the two different kinds of applications. Depends on how what kinds of liquid fuel you mix with water, they will different experience for you. For the gasification mechanism, if you assume, okay, in this case, we just use the 30% water additions, but we meet the first one is the so-called Botrytite group. That means that we mix with the lower boiling point for the liquid fuel, fuels lighter than C9 and C10. Okay, there is, for example, C7 or for example C6. They have a lower boiling point compared with for example C7 or C16. This is a group and of the liquid fuel easier to be evaporate. Okay. And you will find out from the experimental observation, they find out in the burning experience, the droplets remain milky during the combustion, but the combustion usually is terminated by extinction. Okay, I give you the examples to let you know the behavior. This is an experiment that we use a C7 mixed with water. In this case, actually, the C7 has a slightly lower boiling point compared with water. Okay, now you easier to understand for the case for these two cases. When you have a large water, that means the water will absorb more heat without doing any contribution for the heat release. That means that you can see the droplets, the droplet variation, the droplet size variation is most of them follow the D-square law, but for the case B has a shadow gradient, right? It has a small gradient. That means that evaporation constant is small compared with the case A. Okay, case A has a larger slope and they can extend to a longer droplet lifetime compared with the case B. Okay, this is simply explained by the addition of water because you have more water for the case B, then the burning intensity for the diffusion flame is weaker. Then and also they have a shorter lifetime. But you will find out actually most of the cases the droplets the flame disappear at a certain point, and this is caused by previous I already mentioned is terminated by extinction. you can figure out for these fuels. Initially, you may figure out the C7 will start to evaporate very fast. Then the water will replace the C7 on the surface. Water provide the water vapor. This is the diffusion flame will suffer by the water vapor because they come in, they will absorb heat. And finally, you can see when you in the initial period, most of the C7 complete burn out. Then the rest of them just have a water. Then flame will extinction. Okay, at the end of the droplet. Without flame, they still have some the droplet left when the flame extinction. This is the behavior for the volatile group. Okay. Now we change to think about a high boiling point fuel. We say this is a non-volatile group and mixed with the water. The definition is the fuel heavier than the decant or undecant. Now we choose the C16 as an example to mix water. Then you find out the first important thing is in the burning process, the droplets is very surprising. The appearance of the droplets change from the milk to transparent. Okay, that means that you can figure out in the process since you will have some heat transfer into your droplet, and those heat generally they represent some energy add to the liquid. They will improve the mixing of the water with the non-volatile fuel. For this example, is C16. Then the mixing label will reduce to the Armstrong labels. Then the appearance of the droplet become transparent. Okay, this is a first observation and completely different from the previous volatile group. Okay, and the second they tell you, yeah, the droplets will be finished, but usually they finish by the micro explosion. Okay, when you have a micro explosion, the droplets will be broken apart. Then you will not have droplets exist. That droplet exists in the combustion chamber. Then the experiment finished. Okay, and you look at the experiment. Actually, you can see we cannot say this too much difference from the description of the d squared law because there's almost a linear, but in the initial period there has some curve, right? Okay, and they tell you in the initial periods for the C16 because its boiling point is very high, then they still have some heat used for the preheating, and 10% water do not give you too much intensity for micro explosion until the end, very close to the end of the droplet lifetime. But when you increase the water percentage to 30%, then you can see the micro explosion occur is earlier compared with the case of B. Okay, and this is two typical examples to let you know if you use water mixed with different kinds of hydrocarbon liquid fuel, you may experience a different combustion behavior, especially at the end of the droplet lifetime.